Okay, so I have a velocity versus time vector here, or VT graph here. So I want to find the average acceleration from this point to this point. Okay, the average acceleration is the slope. If you have a VT graph, is the slope of the line that connects the 2 points. So I have point 1 here, point 2 there. I connect them with a line, and this line is exactly overplotted on the actual graph. So it's to my benefit, meaning that I have all the information that I need. So the slope of this line, which is the tan of this angle, tan of theta, so the slope, which is the tan of theta, is that side, which is 12 meters per second, divided by this side, okay, which is 2 seconds. Okay, 2 seconds. And I have 12 divided by 2, which is 6. What is the unit? Meters per second divided by second, which is meters per second, or meters per second squared. Okay. And simple as that, really. The slope of a line that connects the 2 points in a VT graph is giving you the acceleration. Okay, now what if I ask you that what is the instantaneous acceleration at this point? Let me just call it 0.3. Okay, what is the acceleration at that point? Then acceleration of instantaneous acceleration of that point is the slope of a tangent line to the graph. So if I try to draw a tangent line to this graph, I will end up overplotting over the graph, meaning that this green line that I just draw and this line, the above line, the other line, will have the same slope. So instantaneous acceleration at 0.3 is the same as the slope of the other line, meaning it is 6 meters per second square. Because they have the same, these two lines have the same slope. And I know the slope of a tangent line is just instantaneous acceleration. So what it means is that they have the instantaneous and average are the same for this case. Okay, so here we have a sample graph. If the velocity is 0, if something's velocity is 0, it's just a stationary, it's not moving, it's staying at the same spot as it was before. So meaning by time equals 1 second, 2 seconds, 3 seconds, and so on, its position is not changing, its position is constant. Okay? There is no graph for velocity because the velocity is 0. Obviously, since the velocity is 0, it has not changed, so acceleration is also 0. Okay? Motion with constant velocity will have a line like that. An xt graph will be in a straight line or a linear relation because the velocity of it is not changing over time. See, the velocity at this point is exactly the same as velocity at this point. There's no acceleration. Motion with constant acceleration will have a curve-looking shape when it comes to xt graph. It will be a linear relation or a straight line for vt graph, and the constant acceleration, meaning that the acceleration at this point is the same as this point of time. Okay? And motion with constant deceleration, meaning that it is losing acceleration, it's not gaining speed, it's losing, decelerating, will have the same type of graphs, but the curvature for those graphs are not the same. What do I mean by that? So here's the curvatures up. See, it is curved like this. Okay. Here's the curvature is up. But the curvature for this one is down. This one has a positive slope. This one have a negative slope. Okay. But the acceleration is constant. So whatever the acceleration is for this point is exactly the same as this point. So motion with constant acceleration. So acceleration is A is V minus V naught, T minus T naught. Okay, just like that, because if you remember, V average is delta V over delta T. Okay, and usually when we start solving the problems, when the motion starts, the time is 0. Okay, when the motion of an object is starting, that's the time when you start to count the time. So usually this T naught is 0, and that's what we get. Okay, if I play with this equation in the box, I can write it as this. I can write it that I can give a denominator of 1 to this, and I can write it as V minus V naught equals to A times T. So just like this. And I solve this for V. Now I have an equation for velocity. Very important equation. What it says is that the final velocity is equals acceleration times time plus initial velocity. That's what it says. For constant acceleration, this is very important. If you have a constant acceleration, that's the one that you're dealing with. So constant acceleration. Constant acceleration means that your acceleration is not changing by time. Acceleration is not changing by time. Okay. Now, the average, and let's do this. So now what I have here, do you remember the V average formula? It was delta X over delta T. And I told you a lot of times, instead of using V average, we just use V bar on top of it. That's the exact same thing here. So take this V average and write it like this. Delta X is V average times delta T. Okay? And that's the formula that we have right there. So V average is delta x over delta t. We also write it as V bar. If I solve this to find delta x, I have delta x equals V bar times delta t, which is right there. Now, that's our point to start. Now, when it comes to something being constant, V average, we can write it just like this. We can write V average like this. Excuse me. So V average is V final plus V initial divided by 2. Or we can write it half of V initial plus V final times t. Now, if I, instead of, so for this t, for this velocity, I can substitute it from the previous slide, from the previous page. I can put that there, okay? And kind of dealing with something like this. 1 over 2 V naught plus AT times t. And I can write it eventually this way. I can eventually write it like that. Very, very important. In other words, if you want to write something like this, so you can say delta x, which was the displacement, is half a t squared plus v naught t. You can write it like that. Super easy. So this is the other formula that we use frequently. Remember the average acceleration was delta v over delta t, average acceleration. If acceleration is constant, its value, its average value and its instantaneous value are the same, so I can write it like this. And delta v is v minus v naught, delta t is t minus t naught. Usually when we start the motion, the time is 0. So what we have here is v minus v naught over t. So that's exactly what I have up here. All right, I solve it for t. So I can find t based on v and a, and then put it on delta x, put this guy right here, okay? And then, so I have 1 over 2 v naught plus v times v minus v naught over a, and I can write it like this. And this is also another very important formula. And I have provided these formulas in the equation sheet for you, so you don't have to memorize all of them. You can always use these equation sheet, but just have in mind that where these equations are coming from. We play with these equations for specific reasons. For example, you might ask, oh, why did we need to do this? If you're looking at this equation that I just highlighted, it is time-independent equation. You don't see any information about the t. So if you are dealing with a problem that has no information whatsoever about the time of the motion, it didn't say, it doesn't provide any information about the time. However, it is giving you velocity, it is giving you acceleration, okay? But you have no information about the time. You can use the time-independent equation, which is right here. It doesn't have time inside. You have velocity, you have acceleration, you can find delta x. Simple as that. Okay. So 5 kinematic variables: displacement, acceleration, which is in our case is always constant. So average acceleration and instantaneous acceleration are the same. Final velocity, which is v, we sometimes show it with v final, we sometimes show it with v2. Initial velocity, v naught, we sometimes show it with vi for initial, or v 0 or v naught, as you can see here, or v1. Okay, and time, t, and delta t sometimes, so it is t2 minus t1, or it's better me writing it like that. This delta t, or the elapsed time, is t final minus t initial, t minus t naught. And usually when we start the time is exactly the time that the motion has started, so initially the time is 0. So that means delta t is just t right there. Okay. So these are the equations of kinematics for constant acceleration. You are not dealing with variable acceleration for this course. Okay, variable acceleration is difficult. We're not dealing with it, so don't worry about it. Every problem that I am assigning to you for this course will be in a constant acceleration. When the acceleration is constant, these are the set of equations that you're going to use. And as I said, I have provided them in the equation sheet for you, so you don't have to be worried about them. V equals AT plus V naught. Delta X is average velocity times t. Time independent equation is here. There's no information about the time here, okay? And delta x, which I would like always to write it like this: half at squared plus v naught t, okay? Kind of like that. So you'll see what I'm talking about once I start solving some problems for you. But so reasoning a strategy for solving the problem is that you have to make some drawings. Decide which direction is called positive or negative. Remember, the direction of the motion of the object is always positive. Write down the values that you have. Write down the things that you know. For example, any information that is given to you by the problem. It is a ball is started from a 0, velocity of 0, meaning that initial velocity is 0. It is started at times equals 5 seconds, meaning that initial time was 5 seconds. Write those down. Everything that the problem is giving you, write it down. Okay, now you have a bunch of information and bunch of unknowns. You have the equations in front of you. It is your responsibility to look at the equations and look at the things that you have, the problem has provided for you, and figure out the unknowns from the equations. Okay, it is not really difficult. It needs practice. It needs some sort of practice so you can get it done. So once, if I am solving a problem, I will draw a box on the left side and I start writing whatever I have. Do I have the velocity? Yes, it is like 20 meters per second, for example. Do I have time, initial time? Yes, it is 0. Final time? Yes, it is 10 seconds. What am I looking for? X. The problem asks for me where the object is located. So I'm actually looking for its position. So I'm looking for X. Now I have all the informations. I go back to my equation sheet and I try to figure out to find X based on the equations and the things that I have. Okay. So it is also important to know that when a motion is divided into segments, remember that the final velocity of the first segment is initial velocity of the next or the second segment. And also remember that there might be two possible answers to a kinematic problem. Freefall. Freefall is also a motion with constant acceleration. Motion with constant acceleration. These are the set of formulas that I have, okay? Free fall is a motion of constant acceleration. But remember, free fall is something is falling down freely without any air resistance, without any force. It is freely falling only due to gravity, okay? Only due to gravity. So if you hold your pen up and you let it go, it'll fall down to your floor. This is not a free fall. A free fall should meet these two criteria. In your room, you have air, so you have some sort of an air resistance. So the free fall does not apply. It is very close though, but it's not 100% because you have some sort of an air resistance in your room, okay? Important to know that free fall is a type of constant acceleration motion, is a type equation of kinematic with constant acceleration, is it has a constant acceleration associated with it, okay? And the acceleration is 9.8 meters per second, okay? 9.8 meters per second, and that's what we call G. So if you're dealing with a free fall, your A, or acceleration in your problems, is just G, gravity, which is 9.8 meters per second squared, and it is constant. Okay, it is a constant value. 9.8 meters per second is your G. If you are dealing with free fall, and it is constant, it does not change. So the rate of the acceleration is based on the gravity of the Earth and is always constant no matter where you are. So for example, if I am dealing with a free fall problem, and I know that this is a constant acceleration. So I am dealing with these bunch of formulas, but instead of A in these problems, acceleration in this set of formulas, I am simply just using G. Okay, so if you were solving a problem and it says an object is freely falling from a top of a building or whatever, then you immediately know, oh, it's a free fall. A free fall means constant acceleration, but this time the acceleration is due to gravity of the Earth, and it's always 9.8. The value of it is always 9.8, and it's always towards the Earth center. So for example, if I have this being the Earth, well, it's right there, being the Earth, the acceleration is always towards the Earth center. So if you're there, it's always towards the Earth center. If you're here, it's always towards the Earth center. If you're here in the southern hemisphere, for example, it's always towards the Earth center. It's always down. Kind of like that. Okay, so at times if something is dropping, something is freely falling, at times equals 0, the velocity is 0. I let the object to freely falling down. I let the object to fall down without any air resistance. At t equals 0, right there, okay, t equals 0, the velocity is 0. T equals 0, velocity is 0. You let the object go. At the initial time, the velocity of it is 0. 1 second later, remember what the G was? 9.8. In fact, you can show it as 9.81 to be more accurate. Meters per second squared. And it is a vector, by the way. It's always towards the Earth. So 1 second later, it has gained this much of a speed, 9.81. 1 second later, it has gained the same amount of a speed. So I have to add another 9.81, which is 19.6. 1 second later, it has gained the same amount of a speed. It has gained 9.81 of a speed. So now I am at 29.4. 1 second later, I gained the same amount of a speed, 39.2. Okay, so I have to add each time from second 1 to 2, I'm adding 9.81. From 2 to 3, I'm adding 9.81. 3 to 4, I'm adding 9.81. Okay, because that's the meaning of acceleration, changing of a speed. Okay, the speed was 0. 1 second later, I have gained 9.81 of a speed. So 9.81 meters per second per second. Each second per second, you are gaining 9.81 meters per second. Okay, so in other words, if I want to be clear here, so let's take a closer look at this. So t equals 2, the speed is 19.6 meters per second. At t equals 3, the speed is 29.4 meters per second. You are gaining the 9.81, okay, meters per second of a speed in 1 second. So that's why the acceleration is 9.81 meters per second in 1 second, or per second, or per second square. Okay. Okay, this is the end of chapter 2. I'll start working some problems, and if you have any questions, you can let me know. You have my email, you have my office hours, so come and ask questions if you have any.